By the way, so after this electrochemistry class, one additional class will be about molding, all the different types of plastic molding that are out there. And then the last class will be what my group here at UC Irvine is doing with all of these techniques. It's kind of like a review of all research projects within the BioMEMS group at UC Irvine. That's the remaining stuff we need to deal with. So we did go over electrochemical grinding. Remember, that's using a mechanical wheel that does not only do mechanical grinding down of your workpiece, it is also electrified. And because you put a charge between your workpiece and that wheel, a big charge of the removal of material, a big part, is electrochemical rather than mechanical. Actually, 90% of the removal is electrochemical, 10% is mechanical. That means that these expensive wheels last much longer. So that's the older form of electrochemical machining, ECG. But we had arrived at ECM. So this is ECG. Here you see a bunch of these wheels that are being used in electrochemical grinding. And then in electrochemical machining, very much like with EDM in a way, and there's actually quite a few similarities between EDM and ECM. And let me ask you that. That's not a question that I would ask in the final, but just as a brain teaser. What would you do to convert this thing from an EDM machine to an ECM? I wonder how many people know that. Don't shout it. If you know it, raise your hand. So you remember EDM, right? Electro-discharge machining. And now I'm saying, look, I have this machine here, and I'm doing ECM with it. What would I need to do to turn it into an EDM machine? How did that work in EDM again? In EDM, you also had, your tool is the opposite shape of what you're going to be making, right? Same thing. And then you push that tool into your workpiece as you're corroding away material. Now, what is the big difference here between these two setups? Yeah.
You put fluid from a conductive fluid to a
Very good. That's one big point. So instead of a conductive solution with sodium chloride or sodium nitrate in it, you make that DI water or oil, right? And so what is the consequence of that on your power generation? So that's the next thing. You will have to apply a much bigger voltage, right, till you get breakdown. But that's good when you're studying this to kind of recognize what is the key differences between these two techniques, because superficially they kind of look the same, except pretty sure that the power supply here, your DC power supply, couldn't do the sparking either, right? Because you remember you use small pulses in the case of DC EDM. Anyone who remembers why we did this yellow coat on this workpiece?
So you don't machine on the side of the tool.
Very good, right? So if that yellow coat was not there, you would basically eat out also sideways. So you see here kind of a typical ECM machine. These are not small, these are big machines. So it was initially developed to machine hard-to-machine alloys, but also, I mean, pretty much any metal can be machined. Here you can again, be certain you will not be machining an insulator, right? And neither a semiconductor. So ECM is an electrolytic process, and it's based on the phenomenon of electrolysis. So who remembers the Faraday law now? That was kind of like the only little bit of maths we had in this whole class, isn't it? So how did that work?
Mass equals current times time times the weight, gram equivalent weight, divided by Faraday's constant.
Right, so, and the Faraday's constant, how do you get to that? Remember that? Who remembers how we get to the Faraday constant?
Charge per electron.
Shh, wait. I can someone else. Yeah, so you multiply two constants to get to the Faraday constant. You remember those two? You remember? No? So F Faraday is the amount of charge associated with depositing or dissolving 1 mole of a material, singly charged. Right? So if I corrode away in my ECM 1 mole of iron, right, I will have consumed 1 Faraday of charges. Faraday is about 100,000 coulombs. It's 9,600, 500 coulombs. Now, how did we come up with that number? We multiplied 2 quantities, important physical quantities. So 1.6 10 to the minus 19, right? Multiplied by? No. Avogadro's number, right? Right. That's right. You should be very good. Okay. And so this started actually quite a way back in the 50s, and then mostly for shaping high-strength alloys. Now, you know, by the 1990s, this was employed in many, many ways: automotive, offshore petroleum, medical engineering, etc. So it's a big manufacturing tool. One thing that you can kind of recognize, that when you make a workpiece, it will have to be an open structure, right? Because you're working with the negative of, you know, say we machine this, right? You have to have the negative of that, so it needs to be an open structure, right? You cannot have something where there's, let's say, a hole and then it carves back inwards. There's no way you could do that. Huh? It needs to be an open structure to be able to do that. So the tools you're using are typically made of copper or brass or stainless steel, and how will we charge those? So one will be positive and one will be negative. So what are we making positive here in ECM? What is the anode positive? Sorry? No? Yeah, you should know that by now. Let's think this through again. Huh? So I thought we had, so I need to go back to that, because if you don't have this one, we cannot proceed. So to make sure my tool never corrodes, I will always make it, the cathode, I will make it negative. Huh? That's where electrons are being pumped into the solution. And your workpiece, you make the anode, so this is made positive, and this is where the corrosion occurs, right? That's why in the introductory to this class, I gave you some of the fundamentals of electrochemistry, right? Anode, cathode. Anode is positive, that's where corrosion occurs. Cathode, that's where you pump electrons into the solution. That's where reduction occurs, right? And so machining is really oxidation, right? The products that you make here are, if this is iron oxide, soluble, and you remove it. And so this material of the cathode, very nicely, will not be touched at all, because you protect it cathodically, you're pushing electrons through it, so it will not corrode. Huh? So can be made of copper, brass, or stainless steel. And while the most commonly used electrolyte is a concentrated solution of inorganic salts, sodium chloride, for example, right? The DC power source charges the workpiece positively, so we have it here again, and charges the tool negatively. And then the machine slowly brings the tool and the workpiece close together, perhaps to within, let's say, 0.01 of an inch. And the power and electrolyte flow turns on, and you start machining into your workpiece. The electrolyte is recirculated, so it also serves a purpose of making sure you don't accumulate anything on the cathode. What could accumulate on the cathode? I want to see if, back to that electrochemistry, I want you to have some of the physics and fundamentals of this process. So suppose this is, going back to the drawing, here. Suppose this is iron. What could deposit on the cathode if I don't flush stuff away quickly?
Oxidation.
No. Hey, you guys still don't get that, huh? I have to be careful here. So what could, so this is iron, right? I make this the anode, and I make this the cathode. So try to write the reactions down. Could you do that? So make it very simple. Write a reaction of iron going to iron 3+, right? Because you're stealing electrons You're making the anode, and these electrons you stole are going through the circuit and are fed into the cathode. And so this guy wants to give off electrons. Where can he give the electrons to? Iron 3 plus could indeed be reconverted, and so everything you corroded on your workpiece, you could redeposit it actually on your cathode. But if you flush the material away, it doesn't have the chance to deposit. What else can happen then if I can't deposit iron? What could deposit instead? You're in a water solution. What do you think? What could happen? So where could these electrons go? Say? They could reduce protons and they could devolve hydrogen, or they, like you suggested, they could reduce oxygen, right, and go to OH minus. And that would really do anything, it wouldn't upset the process, right? But the current needs a path, right? So I'm kind of amazed that these simple things you cannot answer. So let me dig into that a little bit deeper, because the most profound thing you need to know out of this class is how the electrochemical process allows you to do machining, right? So let's go back to some basics. I cannot stand that you cannot answer these simple questions. So if I have my workpiece here, it's iron, and I have a cathode there, there's a gap here, right? This gap is water with some salt in it. Now, why, in this case, can an electron not move through the solution and directly to the metal? Just think very fundamentally, physics. Why is that? So I have two electrodes, an anode and a cathode. Why doesn't the electron go into the solution and go from this electrode to the other one? Because an electron cannot survive in water. It will be immediately picked up by an ion. So what is a more logical way of connecting the anode and the cathode? It's an ion moving from one electrode to the other one. Are you guys following that? This is amazing quiet today. There seems to something depressing happen to you guys. Is it the finals coming close? Or come on. We need some spunk here. So I'm an electron, okay? And here is the solution. I cannot jump in the water, I'll die. So what do? I take a taxi. The taxi is an ion, for example, iron 3 plus. Iron 3 plus, it has a seat. There's a vacancy there. So I jump onto iron 3 plus, I'm in the taxi. The taxi now has become iron 2 plus. Only 2 more passengers can come in it. But here, iron 2 plus now, I can move through the solution and I survive. So to complete a circuit in electrochemistry, you go from electrons to ions. Okay, one more example. Who knows the famous Potato Man experiment? Who has seen that? Or an orange. You take an orange and you put 2 nails in it, a copper one and a zinc one. And you put a little lamp on there between these 2. What do you think you will see?
Lights up.
It will light up. So what does the potato or the orange do there? It provides the path of the ions going from the anode to the cathode. Same thing. So when we were asking earlier, what will happen on the cathode? Well, these taxis, these ions, right, they can either go from the anode to the cathode or they can be flushed away. There's a drain breaking and all the taxis are flushed out of the road. Now the only thing left to happen, there's still water there, and the water can be converted into hydrogen because electrons jump on the protons now because the iron has been flushed out. Are we okay with that now?
So is that safe to say that there's a given flow rate that you want to reach
Yeah.
in order for...
Right. And you still almost certainly will deposit some material. There's no way you could flush out everything. But you don't want it to grow that fast because if the iron accumulates here, you might shunt it, right? If some metal grows on here so fast that it contacts your workpiece, what will happen with your voltage? It become Zero, right? You shunt the whole thing. Good. So the first bullet point, we said it already, electrochemical machining historically followed ECG. ECG is with that wheel, right, grinding. And ECM, one employs a cathode electrode shaped to provide a complementary structure in an anode workpiece. Again, this is very much the same as in the case of EDM. And you answered how actually you would convert one to the other one. A highly conductive electrolyte stream separates the cutting tool from the workpiece, and metal removal is accomplished by passing a DC current of up to 100 amps per centimeter square through the salt solution. As the cathode tool approaches the anode workpiece, it erodes and complementary shapes is created in it. Thus, complex shapes may be made from a material such as a soft copper and used to produce negative duplicates of it. And so that's nice, right? Because it means your workpiece, you can make in a very easy to machine metal, let's say copper. But then your workpiece is a very hard to machine material, right? And so, but with electrochemistry, hardness of no consequence, right? So very easy to machine copper generates this complex shape in your workpiece. Then the pressurized electrolyte, again concentrated solution in organic salts, passes at high speeds. You were asking about how fast. This is indeed quite flushing it through very fast, 10 to 60 meters per second through the gap, which is about 100 to 600 microns. That's a small gap between the workpiece and the tool to prevent metal ions from plating onto the cathode tool and to remove the heat that is generated as a result of the high current flow. How would you calculate the heat generated here? I want you guys also to have a broader kind of physics understanding of all of that. Suppose you work with one of these ECM machines and you need to calculate from an engineering point of view, you know, how fast does the heat accumulate in that gap? How would you calculate that? What equation would you use? I hear a lot of cursing here. Oh, shoot, I know that. What would you do?
I mean, it goes back to fluids and thermal. But
it goes back to fluids and thermal, right? But a very simple equation that you would use, because you have an I, a current, right? How is that related to power? You would start with seeing how much power are you pumping in it, right? So P, power in electricity, relates to current as?
P equals IV.
What?
P equals IV, current times voltage.
No. R squared? Yes. I square R. Again, I'm not going to ask that, but you know, you should start getting some of these fundamental concepts in your head. You know, when you become a scientist or an engineer, is when you start having a few little equations in your head that very quickly allow you to reason problems through. And you must be able to do it as good as you speak your common language. And then you start feeling comfortable because you don't have to remember that much. You know, there's a few constants, like we were talking about Faraday's constant, or how to calculate the power. You need to know so few constants to generate correct answers to questions like that. It's actually a lot of it has to do with confidence and being faced with real problems and feeling the satisfaction. I licked that one, I solved it, I understood it. You know, that gives you a good feeling. You know, I'm going to tell you a story. My first consulting job ever, and I think I was 27, was the following. I want to see if one of you guys could figure this one out. So there's a big company in the Bay Area. When I came to this country, I first lived in the Bay Area, Palo Alto. And there was a company close by. They do electrophoresis. Now what that is basically electrochemistry. Basically you have an anode and a cathode, right? And you apply a big voltage between the two. In that case, because you want to separate things like DNA, right? And they will actually move depending on their size from one electrode to the other electrode. Now, in their experiment, they had on a metal bar, a plastic metal bar, they had a metal stirrer about 1 centimeter long. And what they would see, that stirrer would violently develop gas on the stirrer. And I looked at it, and I did one move with my hand, and I stopped the stirring. I'm still so proud of that. First of all, why would there be gas? So I want to drill in some electrochemistry in your brains. Anode, cathode, right? And I have an electrolyte in this case, and I apply a big voltage between the two. So now, I have a metal bar not connected with anything else in there, 1 centimeter long. And that metal bar develops hydrogen and oxygen on its ends. Why is that, first of all?
Electrons are rushing off the bar into the liquid.
No. What is present in that electrolyte between these two electrodes? There is something there. It's called a field, right? E. Now, the field is given by, what is field? E. The equation for that is V over X, right? So voltage over distance. Now, you remember when I started talking about electrochemistry, one of the first experiments we probably all have done is splitting water, right? Hydrogen and oxygen. Now, how much volt do you need to create hydrogen and oxygen? About, theoretically, 1.23 volts. In practice, 1.5 volts. So if you have two metal electrodes and apply 1.5 volts, you will have hydrogen on one side, oxygen on the other side. Now connect that to my experiment here. So that's that stirring blade, it's about 1 centimeter. And it devolves hydrogen and oxygen. So I want someone to see, to do the right, so the electrodes are like this, and the stirrer is like this. And you need to do one move with your hands, and you will have, yeah, you got it, $1,500. That's what I got for that. That makes you feel proud. Did you see what he did? Show it. Yeah, you see, the field is like this, right? And so my metal part of 1 centimeter long is oriented like this. So there's enough X to create enough field to create hydrogen and oxygen on this structure. So what you do is, you do it like that, and voila. And
hydrogen was being formed on one end of the stirrer,
yeah,
and oxygen was being formed on the other.
Correct. That's right, yeah. Because you have enough distance, right? And the voltage over that creates enough field to get to 1.5 volts, probably quite a bit more. And so all you needed to do is, exactly. And so these little things have nothing to do with you understanding all of the nitty-gritty of electrochemistry, but it's understanding some very fundamental principles. The field strength, what electrons do, what ions do, etc. So the cathode is advanced. The cathode is the one we make negative, right? And could be the soft material into the anode workpiece at a rate matching the dissolution rate. That makes sense, right? You can only machine as fast as things are being corroded out, which is between 0.5 and 10 millimeter per minute. High current densities though, eh? That's why you can have that heat produced, because normally in an electrochemical cell, well, you know, you have batteries, right? You have to draw a lot of current before it becomes hot, before it heats up. But once you talk about 10 to 100 amps per centimeter square, you sure have a lot of heat there. So supply voltages are pretty low, right? 5 to 20 volts. And the lower values being used for finish machining. Well, that's another tool. The roughness of the part will actually depend on the size of the current. So if you have higher current, your workpiece will be carved out with rougher edges. Then reducing the current, you will have smoother surfaces. So actually, the cutting speeds and surface finishes are somewhat comparable to those of EDM. So and the rate of material removal is the same for hard and soft materials. We already guessed that, right? And surface finishes can be as good as 0.3 to 1 micron. Cathode tool characteristics must be machinable, of course, high Young's modulus, but not that high. Copper is good enough, right? Be a good conductor and have good corrosion resistance, but that would only be a problem when? I want to see if you can answer this one. Now, by now, you must know that. the tool would only be subjective to corrosion when? No. So normally the tool is negatively charged, right? So as long as it's the cathode, it will not corrode. But if you by accident, change the polarity and you have this expensive shape tool, you still might want it to last a little bit while anodizing it by accident. So the three most common cathode materials used, we said that already, are copper, brass and stainless steel. And because there is no actual contact between the tool and the work, the tool does not have to be harder than the work, as in traditional machining methods. So this is one of the few methods to machine very hard materials, and another is, of course, spark, discharge machining, or EDM, which we knew already. Some advantages, and so here you could expect a question in the final from this list here. So components are not subject to either thermal or mechanical stress. Thermal is only true. That could be one, if you say true or false, right? You might want to fine-tune a little bit. So if I say not subject to either thermal or mechanical stress, mechanical, it's easy to understand why it's not applicable, but what about thermal? That is if you flush enough liquid, right? If you have enough cooling there. There's no tool wear in ECM unless you by accident make it the anode, right? Your tool. Non-rigid and open workpieces. Open workpiece you understand now, right? So you cannot electrochemically kind of carve behind an angle. Non-rigid and open workpieces can be machined easily as there is no contact between the tool and the workpiece. Complex geometrical shapes can be machined repeatedly and with accuracy. So it's a time-saving process when compared with, so it's faster than CNC machining. During drilling, deep holes can be made, or several holes at once. That kind of makes sense, right? So you could have a tool that has 15 drills, so to speak, that move into the surface. Okay, the third bullet point on the right. Do you know what that means? ECM deburring. What is burring? So when you got the CNC machining class, did Steve talk about burring, burrs? So it's these rough edges you have on the corners. And that is nasty because that means that afterwards you have to polish them off or get rid of it. With electrochemical machining, you have hardly any of it. And actually you can use it for deburring. So you could have a mechanical machined piece and there's burrs on it. You then do a short electrochemical anodization, you can get rid of the burrs rather than you having to polish over them. So that third bullet point makes sure you understand. Fragile parts, which cannot take more loads and also, or brittle, tend to develop cracks during machining, can be machined easily in ECM. That makes sense, right? Brittle materials, they don't care. There's no mechanical force on it that would cause them to stress or crack. And so the surface finishes of 25 microinch can be achieved in ECM. Enough about ECM. And I'm going to close off with a table where we're going to compare three of the principal machining techniques we've seen this quarter. And it's comparing EDM, ECM, and conventional mechanical machining. And in this table, you will see it's on the next slide, a very critical parameter is always MRR, that's how fast do you remove material, material removal rate. Tolerance, surface finish, damage depth, and required power. Of course, I will not ask specific questions on that with numbers, but I might well ask how they compare with each other, crudely. Which one is the faster? Which one is the cheapest? Which one is the easiest to invest in? Because it's a small startup investment. So here we go. We have ECM, second EDM, and then CNC. And so first, we are comparing the metal removal rate. That is in millimeter cube per minute. And so the fastest, I don't know if that's what you had expected. What had you expected? So the fastest is CNC machining, right? And then the next is ECM. And the slowest is actually EDM of the three. Then tolerances, so in terms of what kind of dimensions you can achieve. CNC, they say 50. Remember my rule of thumb in the beginning of the class was 100. It's about 50 to 100 micron. With EDM, 15, and with ECM, 50. So in that sense, in terms of tolerance, EDM is actually the best. Kind of a bit surprising. Then the surface finish. That's how smooth the surface you end up with after these processes. Damage depth. Could anyone explain that, why the damage depth is the worst with EDM? Right, so if you look at damage depth, and do you have another word for that, damage depth? Something that relates to that? There was another word. No? Yeah, HAZ, heat affected zone, could correlate to that because you can see not all of them are thermal techniques. But EDM has the highest damage zone. Any kind of feel why that might be?
Higher voltage.
Sorry?
Higher voltage.
Much higher voltage, right? That sparking creates locally like little heat bursts, right? So very good. And then the power consumption here, you can see the most costly, and this is kind of one of the banes of electrochemistry. Electrons are expensive. You see that, right? In ECM. 100,000 watts. Enough for that. We're now going to very briefly, you can forget about this, and I'm going to go quickly about this micro ECM, because the principle is all the same except this. Suppose that instead of having my tool, my cathode tool, being in the shape of my workpiece, the complementary shape of my workpiece, I use a very small tool, like a needle. And then I make that a cathode, and I write with that cathode any shape I want. We've seen that somewhere else. We've seen that in some other machining techniques, where instead of making a cathode the complementary of the workpiece, we've seen other techniques that I can do that simpler. Exactly. Wire electrodischarge machining, remember? With that, we could create any shape we wanted without needing to create a cathode in the complementary shape of your workpiece. So same in electrochemistry. You can make a very small tool. So this is just this ball here. That's the only structure that does the machining end. Electrolyte is flushed between this shield here, and this shield is necessary. Why? We've seen this already before. It corresponds to something we saw in this class. We need a shield because you don't want the field line sideways, right? You just want it where you are. You want it in depth, right? So the tool may, that's rather obvious, right? You would connect that tool to a CNC machining, and in a way then it's a combination of all the coordinates that you can control with your CNC machine, but you don't do any mechanical damage, right? But you can use it to contour and machine electrochemically. Neat, eh? So you can make very complex shapes with just one small tool. What are the differences between the two? Well, number one, in conventional ECM, the gap between the cathode tool and anode workpiece is about 150 microns. In micro ECM, it's more like 15 to 20 microns. That makes sense, right? It's much smaller tool, so you can bring it much closer to the surface. It's about 10 times smaller. Now, the major challenge in moving from conventional ECM to micro ECM domain is to control the size of the reaction regime. And we saw that already, right? To control that regime, you kind of try to protect it sideways so that only one small part, as small as possible actually, does the machining. But then there's a counter argument. The smaller that part that eats things away, the slower the system will be, right? So you can already see this might work very well in the lab, but it will be slow, right? So to make this a mass production kind of method might take some more efforts. So methods to accomplish this improvement, to move from conventional ECM to micro ECM, so reduce the size of electrodes, and you could use actually micro EDM to make your tools. Shield the electrodes for stray currents, we saw that already. Then the gap, right, controlling it at 10 to 20 microns. By the way, how do people typically control these gaps? Do you know that? So if you need to control, let's say, I'll go even more extreme, instead of 10 to 15 microns, and actually it's going to be the next slide. Suppose I have this surface and my tip is now not this microneedle tool, it's the tip of an atomic force microscope. And so now this atomic force microscope tip goes over this surface, and I need to control that distance of that tip always within, let's say, 1 or 2 microns. How do you do that? What are the techniques that people use to do this? Do you know?
Some sort of feedback.
You need a feedback, and the feedback comes very often from a laser that you make hit the top of this beam. So if this beam here has the needle, and there's a current between the surface and this needle, and this current is exponentially dependent on the distance. What you do, that current size you feed back into a piezoelectric, and the piezoelectric keeps it always at 1 or 2 microns, because a small change has a huge consequence for the current. You feed that back in the piezoelectric, and the piezoelectric keeps on hovering always 1 to 2 microns. That image you can translate into an image of the surface, and that can be atomic scale. Right? So that is how an atomic force microscope works, and how an electrochemical microscope works. Because what you could do, you can take your AFM, and you can convert that in a machine that just does like that, like this thing, except it's even closer to the surface. Instead of 10 to 15 microns, it's perhaps 1 to 2 microns. And so this is this setup here. With scanning electrochemical microscopy, you kind of have defined the next step. We had ECM, then we have micro ECM, and then the ultimate is really scanning probe microscopy, where your probe tip is now literally, you know, in the micron size range, or less than a micron, and where you can corrode a hole, and at the same time on your screen you can actually see it. You can corrode lines, you can write, and you can see what you're writing. That has not been attempted with micro ECM. Couldn't work, but with this it can. Why is that? Because in this case, this current between the tip and the surface is quantum mechanical tunneling. And so the current size is extremely dependent on the distance. And so it's an exponential curve. And so you can see, that's back to that control loop, if my probe by accident, instead of 2 microns away from the surface, it's 1 micron, the current shoots up by a factor of 100. And that is a tremendous feedback to the piezoelectric, so, oh, pull back. Yeah, remove yourself over 1 micron to always keep at the same current. Right? So that is that controlled feedback, and that's exactly what you do in all of these scanning probe microscopy techniques. I will introduce 2 more electrochemical techniques before quitting it for today. And both have to do with using jets of an electrolyte. So if I have, let's say, this as a metal piece, and I have a jet of impinging liquid on this metal, I can still do electrochemistry, but I define the electrochemistry by the size of the nozzle. In this case, this IBM logo here, and you can see the dimension, there's 1,000 microns, is really written by jet electrochemical machining. You have literally, think about your inkjet printer, the nozzle of that. You use that to eject a stream of liquid, and that stream of liquid will only corrode the metal away where it has hit the material. Of course, now you could say, but that liquid will spread out. You need a mask, right? So you put a mask over it, and then the electrochemistry will only happen in the holes of the mask. Right? So thin film patterning by maskless EMN may be accomplished by highly localized material removal induced by the impingement of a fine electrolyte jet emanating from a small nozzle. And so the next thing we're going to do, I'm going to combine this liquid jet with laser machining. So that liquid can now act as a waveguide. And in that waveguide, I'm going to put a laser light. And this was also developed at IBM. So this is a specimen that I want to etch. This is the nozzle, so same like before, except in this case, with a lens, I focus a laser beam into the liquid stream, and you make it such that the laser beam does not emanate from the jet, so it acts like a waveguide. Now that surface bombarded with that light and doing electrochemistry at the same time, you had a huge increase in efficiency. If you might etch something before, you know, at rate 1, this will be 100 to 1,000 times faster. Same for plating. You can do this for etching very fast, but also for plating. Let's say you want to write with this machine copper lines or gold lines. You just put in your solution the right metal, and then your workpiece will not be the anode, it will be the cathode, right? Because you're now depositing the metal. To have huge deposition rates, the heating of the laser locally on the substrate increases that rate dramatically. So it's a very, very good way of very fast etch rates. For example, for stainless steel, etch rates of 10 micrometer per second have been demonstrated using laser-enhanced electrochemical jet machining. So water jet etching, yeah, forget about that. This is separate. So all you need to know is electrochemical jet etching with a laser. Probably some of you know water jet etching by itself, and you don't use the electrochemical technique as mechanical, right? So if the only thing I'm using is the force to cut cheese with very hard pressure of water, right, that's water jet machining. So don't confuse it, that's what that other bullet is about. Water jet etching is a mechanical process. So that is it for today. So Thursday, no class, and then the rest of the material will involve two things. One will be plastic molding, right? So that is where you will learn about different ways of making plastic goods. And the final class will be a review of the research projects we have going on in the BioMEMS team, right? So very good. I'll see you then, not Monday, because Monday is a holiday. So I'll see you next week, Tuesday. Okay.